So we're essentially just saying, this is not, it's not perfectly elastic and it's not conserved, but just by virtue of them sticking together, and then all of a sudden it's shot off the track. So if we're interested in this inelastic portion, we're going to do some rearranging. So we get V3, and what's V3 going to be? It's going to be the final velocity of that second ball. All right, and we're going to use that in our calculation, and you'll see just how I do that. So V3 is going to be equal to M1 V1. And by the way, what's V2 here? The velocity. So, okay, I just need to explain this a little more. So this is V1. It's going V1 this way. V2 is actually 0 because the velocity of the second ball before the collision it's stationary, so it's 0. So we can just get rid of that. But V3 is this velocity of the second ball after collision. Okay. Now, V3 is going to be M1 V1 over M1 plus M2. All right. And we're going to use this final velocity to find the force. So the force is, again, equal to F equals ma. That's Newton's second law. All right. Now F is going to be, in this case, the force that 2 is experiencing is going to be its mass, which is, we'll call M2, times its acceleration, which is known as dv over dt, or delta v over delta t. Okay? And we have a time in here, which is that, that 6 milliseconds, right? So we're essentially just going to say, first of all, what is this delta v? This is the change in the second ball's velocity. So the second ball has V3 minus V2. V2 is 0, but we have V3, right? So we're going to put V3 in here. So M2 times V3, M1 V1 over, and I'm just going to throw this all in, M1 plus M2 times delta t. Yeah, because it's that minus 0 divided by delta t. And then you will be able to get, your force. So this is still staying in velocity format because we're doing mass divided by the same units, kg divided by kg here. And this will be able to get you your answer for force. And you can go ahead and plug those numbers in. You already have the kilograms. You already have the velocity of the first ball, which is 2.8 meters per second. So you just basically plug in for M1, 0.044 kg. For V1, you plug in 2.8 meters per second. For M2, you plug in 0.039 kg. And for the change of time is that 0.006 seconds. And that'll give you your force applied to the second ball. All right, and then number 3 is actually going to be easier. Let's add another board here. So for 4, let's go back here. It's basically talking about a perfectly elastic collision. So this is actually easier than 3. So for an elastic collision, all of the momentum from the first ball is entering all of the momentum from the second ball. So P initial is going to be P final because the first ball is, from what the problem sounds like, it's the first ball stops after collision, so it's going straight to rest. So this would be known as an elastic collision. This is perfectly elastic, and perfectly elastic is awesome because, again, delta P equals 0. So all you do is just plug in your M1 V1, which is going to be one. So M1 is going to be mass 1, V1 is going to be the velocity of the first ball. So it's just going to be 4.1 times 1.9 times 1.9 meters per second divided by mass 2, which is 1.8 kilograms. And this will give you the velocity of your second ball. All right. Well, good luck.